All right, if I can have your attention, please. Good turnout. Fantastic. This is the final talk of the What Physicists Do fall semester. I would like to take this moment to thank both the Instructionally Related Activities Funds and our private donors. Without your assistance, we could not bring in our series of wonderful and talented scientists to speak so candidly about their work. So I think we should all be aware of this, and if you ever want to jot us a note saying how much you enjoyed this series, that's something that we're collating for letting some of the administration on campus know about how important this series is. So I'd like to just take that moment to thank both of those sources. I'd like to thank you for coming out today. I want to mention to people who are enrolled in this class for credit, not those of you attending for extra credit, but those of you enrolled for credit Physics 494, we meet back in this room next week. There are no more extra credit opportunities for other students, but the students who are taking the class for credit do show up here next week for our end of the semester discussion and review. All right, I'm very pleased today to introduce Dr. Claire Poppett. Her degree in astronomy and physics starts off her path with the University of Durham. She got her undergraduate degree there, and then, as she was telling me today, she went off into the private sector for a period of time, but her thesis advisor called her up and said, I need someone to come in and work on this project. And she came back in, and this has been her career since. She is at Lawrence Berkeley Lab, where she's been for several years, and she's now moving, as I just learned, to a more permanent position at Cal Berkeley, staying in the field of experimental astrophysics. And so I often try to, as a person who has emceed and invited people to the series, I try to walk a fine line of bringing in lots of current cultural things. And I would say that this shows that I don't play favorites. It's very infrequently that we have another experimental astrophysicist, but I'm very pleased we have someone who works with hardware here today in astronomy. Her particular expertise is in spectroscopy and fiber spectroscopy, which I'm sure she'll discuss with us today. Her current work is on an ambitious program called DESI. The DESI experiment stands for Dark Energy Spectroscopic Instrument, which uses robotically positioned fibers to measure the effect of dark energy on the universe, I think out to like a redshift of 2.5 or 3, which means to what has in the past been the distant universe, and now it's probably the moderate universe. But she's studying evolution of the universe spectroscopically, which is a very impressive effort. Their program, DESI, is going to look at tens of millions of objects and is really a follow-on, as we said, to some earlier spectroscopic surveys. And we've had people, I was going to mention Connie Ricosi, who talked about the Sloan Digital Sky Survey. And this is really the current state-of-the-art next generation. And so we're thrilled to have Dr. Claire Poppett talk about DESI. Let's welcome her.
Thanks. Okay, that just about covers my talk. Okay, so I'm a postdoc currently at Lawrence Berkeley National Lab. I am the fiber scientist for the Dark Energy Spectroscopic Instrument. This is an instrument that is going to be installed into the Mayall Telescope at Kitt Peak, Arizona. This is the telescope here. It was built in the 1970s, and the idea is that we use the existing telescope on a new instrument and measure dark energy with 5,000 robots. Structure of this talk, I'm going to talk about our ever-changing understanding of the ever-changing universe. One of the ways that we can learn about the universe is by looking at something called Baryon acoustic oscillations. You're going to learn exactly what Baryon acoustic oscillations are. How can we look at these BAO from a galaxy redshift survey Can we do this from the ground? In astronomy, you can do stuff from space, or you can do it on the ground. Pros and cons to both. We're going to do it from the ground using the DESI instrument, which uses robotic fiber positioners. And then in the last 2 minutes, I'm going to talk about everything else that I haven't had a chance to talk about in the 50 minutes of the talk. So first of all, our ever-changing understanding of the ever-changing universe. Now, although this is a ground-based instrument, I'm going to start with a bit of history from space. The Big Bang Theory, first proposed in the 1940s. The first actual evidence from it, signal, was Bell Labs in the 60s. But the first actual experimental evidence came from space. This is the COBE space mission. COBE looked in every direction in the universe and looked for temperature fluctuations. And what it found is that no matter which direction you look, the temperature is about the same. And this temperature is the surface of last scattering. When things hit against each other, they have some temperature, they cause some heat. And this is what we look for, the temperature variations. And they said, look, it's pretty smooth. Everywhere you look, the temperature is the same. This means that you started from a small position and expanded out at the same rate. This is the first experimental evidence we have for Big Bang Theory. But then we launched some more missions. WMAP in 2009 looked at these fluctuations in more detail. And these different colours are the different temperatures. And they saw that actually there's more structure in this temperature map. You can see more structure than the COBE first saw. And then again, in Planck went to a larger frequency range and more bands at higher sensitivity and looked at these fluctuations even more. And this is the first evidence we have of Big Bang. You look at a power spectrum and you can see exactly the size of these fluctuations over different angular scales. So that's one method. This is the cosmic microwave background. This is one method for looking at the early universe. We have more clues. Another space mission. This is Hubble. This is a galaxy with an exploding supernova around it. And the idea with supernova is that you use them as standard candles. So these exploding stars, they all explode with the same brightness. So their brightness gives you a distance scale. If something's further away, it should be dimmer, just like car headlights on the freeway. This is how we use supernovae. This is the Big Bang. The universe expands, and you can look at these supernovae at different distances, and the change in distance gives you the scale of the universe as it's expanding. This is the idea. The first time these measurements were made, 1998, they looked at a huge survey of supernovae, but some of the supernovae they found were 25% fainter, that's further away than they expected. And so they originally thought, Big Bang Theory, the universe expands, it expands at the same rate as it goes. But what they found is that it's speeding up, it's accelerating. So not only is the universe expanding, the expansion is getting faster, and that's kind of surprising. The universe is made of galaxies and all types of matter. Matter has mass. Mass attracts itself. So you would think that as the universe expands, it should start to slow down. And this is the opposite to what they saw. And the theory behind this is that there's some energy pushing the expansion apart. And that energy, because they don't know what it is called dark energy. This got them a nice article in Science. Also got them a Nobel Prize. This is Saul Permutter at Berkeley Lab. Happened to have a photographer in his office as he received a phone call to say that he'd won the Nobel Prize. He wasn't the only one, but he's the only one at Berkeley who won it for this test. But if you ask him, the best thing about his Nobel Prize was his Nobel laureate parking permit, which you need to get a parking spot at Berkeley. So what does this add into our understanding of how the universe started and how the universe is expanding? If we look, this is time along the bottom. This is size of the universe today. Size of the universe. So if we look at today, this is where we are now, and we're expanding. But is this expansion going to expand at the same rate forever? Is it going to slow down and collapse? Or is it going to accelerate? And these are all different standard models. And the standard model has contributions from both dark matter and from dark energy. And depending how much dark matter and how much dark energy you put into the model, puts you on a different one of these lines. So what we want to know is exactly which line are we on, what kind of universe are we in. The data from Sol, the supernovae data, you can see is here. The little dots with the error bars. You can see as you go further back in time, these error bars get bigger, and it's much harder to see exactly which model is our universe, which universe do we live in. So the further we go back in time, the easier it is, if we have smaller error bars, to see exactly what kind of universe we're in. So that's all the supernovae data. We've already looked at the cosmic microwave background. We need another tool to explore this problem further. And this tool that we use is called Baryon acoustic oscillations. It's kind of a difficult concept at first, but actually you can kind of think of it as a ripple in a pond. If you throw a ripple in a pond, a stone into a pond, you get ripples. And if you froze the pond, you could go back at any time in the future, and from the size of these ripples, how far apart they are, you can infer what the pond was like when those ripples were formed. And that's exactly what we do in the early universe with sound waves rather than ripples in the water. And so Martin White, who was at Berkeley, modeled this. And if we have the very early universe and we put in a single perturbation by hand into our model of the early universe, here's our baryon density, our photon density. This is the mass profile. And we're going to look at how this mass profile changes as a function of time, as the time goes forward. So early universe, it's a coupled plasma of energetic photons and ionized hydrogen. We put in this little perturbation, and because it's a plasma, the gas and the photon fluid expand outwards at speeds approaching the speed of light. So we can watch this happen in real time. Stuff goes out, the universe is hot, everything expands at the same rate, all moves out at the same rate. We keep on going. This goes for about 10 to the 5 years. But then finally, the universe cools down. And the universe cools down enough that the protons capture the electrons to form neutral hydrogen. Now this decouples the photons away from the baryons. So you can see that the baryon peak is stalled. This is our hydrogen forming, and the photons carry on streaming out. We move forward in time. The baryons are still trapped in hydrogen. The photons keep going out. And you can see we have this peak. The matter falls back into our original perturbation. And then finally, you can see this two-peaked signal that we get. This is a very physical thing. This is our hydrogen that's trapped. And we use this mass profile. The radius of this shell is the sound horizon that we see in the cosmic microwave background. And we have to look for this two-peaked signal in our observations. So how do we look for this two-peak signal in our observations using galaxy surveys? Now the idea behind this is that if you can look for enough galaxies, those two peaks, they attract mass. So your galaxy should predominantly form where those peaks are compared to everywhere else. So if you look at a certain redshift and you say there's a galaxy right here, the probability that there is another galaxy within that radius of that shell that we saw from the BAO is a lot higher than at any other distance. So you use this as a standard ruler. So you look for this overdensity in galaxies at different redshifts, at different scales. This is one redshift at a different redshift, and you can trace this all the way back to the cosmic microwave background. So it's a two-point correlation function.
Dr. Poppett, I just want to say, I've heard descriptions of the baryon acoustic oscillations before, but this graphically, it's a very difficult concept, but I found this to be very illuminating.
Okay. That
showing the part which decouples, light is free streaming and the matter, and showing it actually come back. Mm-hmm. And so I just thought I'd point out, because this is a difficult concept, but this idea that in the beginning of the universe having the perturbations, these small variations, and then seeing these structures grow and then collapse in them. In this, I feel like in a few slides I've gotten the idea that I can look at the places where there were ripples in the cosmic microwave background and see that that should be an overdensity. And then I should be able to see in that some sort of structure on particular angular scales or angular sizes on the sky. So I guess at some level that's just a statement, but
Okay.
but I wanted to state it because it was so clear,
Okay.
and I thought I got a better understanding of it.
Thank you. So just to be even more clear, let's go back then. So this mass profile, this is 150 megaparsecs. So what we expect is that this distance is 150 megaparsecs where we have overdensities of matter. This is where galaxies should form. There should be a galaxy here, and it should have another galaxy here. And as that distance changes, that's your distance ladder across the age of the universe changing. So these two peaks, obviously this is a shell, and as you go back in redshift, you can trace that scale as you go further back in redshift. Now, what does this tell us? We looked at these three methods: cosmic microwave background, supernovae, and baryon acoustic oscillations. And this is the amount of dark matter we have. This is the amount of dark energy that we have. And this is how these three different methods constrain how much dark matter and how much dark energy there is in the early universe. So you can see our supernovae, our CMB. The constraint that we get from the BAO in this direction really constrains our model nicely. This is the 1, 2, and 3 sigma level. So we know that there's, in this area, those are the numbers that we should be putting into our standard model of how the universe grows. The thing that you need for BAO, it's all about statistics. If you're going to look for pairs of galaxies and overdensities, you can only infer data from them if you have enough statistics. So you want millions of galaxies in order to be able to do this. Now, Redshift surveys, this is survey completion date against how many galaxies the survey collected. These are the early ones on the TDF, on the Australian telescope, SDSS, which Scott talked about, on BOSS. These are the number of galaxies they got compared to first light. Now, here's DESI. We're going to collect 24 million galaxies over this 5-year survey, which initially sounds like a lot of galaxies. But actually, you know, we're on the trend line. So it's got to work. This is Euclid Space Instrument. Now, we talked about BOSS and the data that got. This plot that I showed before, this BAO is the data from BOSS. And here's BOSS and the angular scale. This is a redshift. In here are all of the galaxies that BOSS was able to obtain. It went out to redshift about 0.7. And here are the data they got from Lyman Alpha. And all of this in the middle, all of these redshifts are all missing just because BOSS couldn't target them. With DESI, we're going to fill in this area. So everything in here is an observation that we're going to get from DESI. So you can really see how we're going to fill in the area of redshifts that we're previously unable to get. The Lyman Alpha stops here because as you go that far in redshift, the blue end goes off the end of your spectrograph. So it's just an instrumentation limit as to why the Lyman Alpha stops here and the galaxies start here. So if DESI is going to fill in this huge area of redshift, how are we going to do it? We're going to look at different targets. First, at low redshifts, we're going to look at luminous red galaxies. This is redshift against expansion rate. And this shows the kind of spectra that we expect to get and what features we're going to look at in the spectrograph to say, yeah, look, that is a luminous red galaxy. So we're going to look for this 4,000 angstrom break. And this will give us our low redshifts. Then we're going to get 4.2 million luminous red galaxies. The main part of the survey comes from our emission line galaxies. We look for these 3 tracer lines, the O2 doublet, the oxygen triplet, and H alpha. And because we have to be able to check that this is a doublet and this is a triplet, This drives the resolution of the spectrograph. The spectrograph goes to about an R of 3000, and those are the drivers behind the spectrograph design. And this fills in the huge redshift range that we need. Another thing we can use is trace our quasars, lots of lines to detect. We fill in another big band, but we don't have very many of them. And then finally, the Lyman alpha forest gets us our highest redshifts by using this 4000, this break in the Lyman alpha forest. So here's the redshifts that we plan to get with DESI all the way out. The galaxies go to 2.5, and then the Lyman alpha takes us higher. And this just shows the current data we have. So these are the current data points we have, and this is what we'll get with DESI. And what will this do for us? Again, we're going to look at the different models. Again, this is time, this is scale of the universe. These are all of the different models. The red data is from BOSS, SDSS. The blue data is the supernovae. And DESI, in this area down here, I've blown it up for you, you can see that it's really going to differentiate the different models that we have. The kind of error bars that we get from BOSS up here, we get the same size error bars at those much higher redshifts from DESI. Yeah.
Sorry, is the little black lines in there are the size of your error
That's
bar?
the size of the error bars that we get.
So you're able to distinguish between multiple pasts and futures to the expansion of the universe with those lines.
That's the plan.
Yeah.
So this is the science we want to get from DESI. If we're going to build this instrument, what would go into our instrument wish list? Because this instrument isn't built yet, so you can still have a wish list. We'd want a dedicated survey. We want as many nights as we can get over any given time frame. We want to collect 24 million galaxies, so the more nights you have, every one counts. We want as many observations as possible, which means we have to be efficient, both in terms of downtime and instrument efficiency. And this efficiency, this is one of the drivers for the robotic fiber positioners that I'm going to talk to you about in a minute. We want to have a large field of view. You want to see as much of the sky in one observation as you can. It needs to be massively multiplexed, and this is how many targets you get in one observation. So we have 5,000 fibers pointing at the sky. One fiber is one galaxy or one object. So we get 5,000 observations from one pointing. And the wavelength range capable of targeting objects over large redshifts, the larger the wavelength band in your spectrograph, the bigger range of redshifts you can get. This is our wish list. Now, what is reality? Can we do this from the ground? When you're building a ground-based instrument, you have your choice of ground-based telescopes. Now, here's all the options you can have. This is primary mirror size of all of the major telescopes. The overwhelmingly large telescope was so overwhelming that it was cancelled. Here's the 30-meter telescope. They broke ground for the TMT in Chile just last month. So that's started. Obviously, it's going to be a while before we can put an instrument on there. The European version, slightly bigger, also slightly later. And here's the kind of favourite telescopes, the Keck telescope, 8 or 10 meter, 8-meter primary mirror, Gemini, Subaru. These are the telescopes that everybody wants to use, these 8 and 10 meter class telescopes. But there's tons of smaller telescopes over here that just don't get used very often, these 4-meter telescopes. And just out of interest, so you can put these big telescopes again in scale. Here's the year of first flight against the aperture diameter of the telescopes. Here's our nice trend line with the Mayall, the AAT, and Keck. And then here's this huge explosion we've got with this new band of huge telescopes. So everybody wants to use telescopes around here, but what about these 4-meter telescopes? What can we do with these? Now the new 4-meter telescopes favour fast optics, so they're compact, they're small, about f1, but these older telescopes, the Mayall and the Blanco, built in the 70s, I showed you a picture of the telescope dome on the front page. These are big, old telescopes. They have an RC design, so they've got a long focal length and large field of view, about f2.7. And because they're so big, they can support large instruments at either prime or the cast focus. And just for a bit of interest on the Mayall, if you replace the F8 flip ring, which is at the top, you can support the weight of 4 Toyota Land Cruisers. So we've got quite a lot of scope to put a big instrument on these telescopes. And in 2009, Mike Scholl, who's an optical engineer at LBL, designed a prime focus corrector that could support a 3-degree field of view. Now, 3 degrees, for some context, this means you can look at 35 full moons in one observation. This is a huge patch of sky you can look at in one go, which helps with our large survey. I've mentioned these 2 telescopes, the Mayall and the Blanco. They're both the same design. The Blanco is in Chile, the Mayall is in Arizona. Changing the prime focus corrector is exactly what the Dark Energy camera group did at the Blanco. So here's the telescope. The main mirror is in here. This is the horseshoe, which allows the telescope to move up and down. And when I say replacing the prime focus corrector, it's this area up here that we're replacing. So the light comes down, hits the primary, and goes back up, and this is the prime focus. So they took this top end off, replaced it with a new prime focus corrector. It's a 2.2 degree field of view. So you single image, you get an area of the sky 20 full moons the size of the sky. And they put this prime focus corrector at the prime focus of the Blanco. And this is Dark Energy camera. We're going to do exactly the same thing with a spectrograph. This is the Mayall. I'll flick back so you can see the Blanco. It's kind of similar. They even use the same paint colour scheme. And so for DESI, here's your main mirror, here's the prime focus corrector. We're going to take this prime focus corrector off, put in a new prime focus corrector to give us our 3-degree field of view. So we can look at 24 million distant galaxies. We'll get 10 times more volume than BOSS, which is the Sloan survey. And we'll do this using 5,000 robotically positioned fibers, feeding 10 3-arm spectrographs. And the way this works, light comes down here, hits the primary, goes back up, goes through the corrector. The fibers are here, 5,000 of them, each in an individual robot. The light comes out of the fiber, down the side of the spectrograph, to a separate room. And here's the spectrographs. You've got a man there for scale. This is a huge spectrograph rack. We feed 500 fibers per spectrograph in a slit. So we have 10 identical 3-arm design spectrographs in our room. We'll talk about that more later. But I realize people don't know this. An optical fiber is a piece of glass about the diameter of your hair. So these are, tiny little tubes of glass feeding galaxy light from the prime focus to our spectrograph. The diameter of the fibers we're using are 107 microns, which is pretty tiny. So that's an overview of DESI. Now, I'm an instrument scientist, so I'm going to spend a lot more time on the instrument design than I did on the science. So here, everything in blue here is what DESI is replacing on the Mayall. Obviously, the telescope already exists. Then everything in blue is what's going on. So here's the prime focus corrector. The top rings all being replaced. Here's the fiber run. We have some cable wraps so that as the telescope moves, we don't snap the fiber bundle. Need some flexibility. And then here's the spectrograph. So the first thing I'm going to talk about is this prime focus corrector, since it was the driving force behind the beginning of the instrument. The corrector optics. We've had over 20 designs of corrector optics over four different groups: Mark Ackerman, Livermore Lab, the Arizona group, and also UC Berkeley Space Science. And we finally have a design. It's got 6 elements with only 2 glass types, which is important when you're asking a vendor to make it for you. It's got a 3.2 degree field of view. And I think the most interesting thing about it is this atmospheric dispersion corrector. Because we're looking at so much of the sky, we go really far towards the horizon. And so just like sunset, when you get the spread of light, this also happens in our instrument if we don't correct it. And so this is what, as we go to 30 degrees from the horizon, if we didn't correct for the light, This is what it would look like at our focal plane. This is 1 fiber diameter. So you can see we'd have a lot of loss of the spreading of the light. And how we correct this, we have atmospheric dispersion correctors. These are 2 lenses which rotate against each other, and they introduce chromatic aberrations opposite to whatever the atmosphere puts in. So you can oppose the atmosphere chromatic aberration with these 2 lenses and bring all of your light back down into a spot. So that's important. So the light comes in from this side, through the first mirror, through the ADCs, and then this is your focal plane. So you put your 5,000 fibers at this focal plane back here. Now people first look at this. This is a meter. So this is a meter lens. That's pretty big. But if you compare it to dark energy camera, you can see it's actually the same size. This is made, it's built, it works. So DESI, we're not too worried about it. It's the same groups working on DECAM who are working on DESI. University College London are aligning all of the optics. Fermilab are designing the barrel, which is the same as the group for DECAM. So the corrector, now that we have a design, it's kind of low risk. Next is the spectrographs. Use the spectrographs down at the bottom of the telescope. Now, I said before, we have 10 spectrographs. You can only feed 500 fibers into one spectrograph, otherwise your optics will be too big. This is our standard sized man. This is a CAD rendering of the spectrograph, but I'm going to show you an optical layout before I describe exactly how the spectrograph works. This is the optical layout. So here's the fiber slit head. The 500 fibers come out of the screen in a slit. The light comes this way, hits a collimating mirror, goes back. We have 3 arms to our spectrograph for the 3 different colours, and that improves our efficiency. So if I just follow the near-infrared path, the light passes through the dichroic, hits a grating, which gives us our dispersion, and then we have a camera to bring the light onto the focal plane of the CCD. Similarly, the light comes from the collimator, reflects off the dichroic, and we send it off into the blue and the red channels. The near-infrared and red camera are pretty similar. The blue camera is a bit different. The thing that I think is the most interesting about the spectrograph, because it's the bit that I worked on, are the gratings. You notice these gratings are working in transmission rather than reflection, which means you have more space within your camera. And we looked at the spectrograph. We looked at all different designs. We looked at reflective versus refractive for both the camera and for the spectrograph. And we also looked at whether we could just do 2 channels rather than 3. We're replicating this spectrograph 10 times. So any shortcuts you can make without affecting the performance save you a lot of money. This is the efficiency. This is wavelength. We go from 360 out to 980. This is the efficiency just from the gratings. So if you have a 3-arm design, here's our 80% level. We're above 80% over most of the spectrograph. If we go to 2 channels, the efficiency is much lower. So that's why we go with a 3-arm design. And these gratings are really interesting. Normally with gratings, you actually physically rule lines on a blank, and that forms your grating. These, we use volume phase holographic gratings, which are gaining a lot of interest in astronomy over the past maybe 5 years. The way they do it, they have a bit of glass. They put on some dichromated gelatin, and this is gelatin which reacts to light. They shine on an interferometric pattern, and then the light and the dark in the interferogram change the refractive index of the gel. So now you've got this gel structure with changing refractive index, just like the rulings you would make in a normal grating, and the changing refractive index, that gives you your dispersion. And you can change all the things like the thickness of the gel or how much you change your refractive index and tune the efficiency to your wavelength band and to your resolution and all kinds of things. Obviously, it's an organic substance. It's a dichromated gelatin. And that drives how we buy the gratings, and when we buy them, we're buying 10 of each one as a kind of side interest. When Kodak had dichromated gelatin in their cameras, they had their own pig farms, so they could feed the pigs a certain diet, so their hooves were nice and consistent. grating manufacturers from astronomy don't have that kind of money to have their own pigs. So we buy all of the red gratings in one go, so that all of our gelatin's the same for all of our red gratings, all of the blue gratings in one go. And you can model the efficiency using a rigorous coupled wave analysis program. And this is really useful in our early instrument design. We got to play around with all of the parameters and see how it affected our instrument. Here's some calculations from this. In gratings, the delta beta, this is the range of angles that come out of your grating. It's kind of intuitive to think that if you have a large range of angles that coming out, you have a flat response curve. If you have a short range of wavelengths coming out, you have a much more peaked curve. And this is the range of angles that come out is related to the size of your grating. So this is gratings getting smaller as delta beta gets bigger, and here's your efficiency. So we played with modeling gratings of different sizes to see where we kind of stopped gaining by having a bigger grating. Bigger gratings are more expensive, they're a more expensive camera. So you can see kind of here, after you get, corresponds to about 6 inches, you don't gain very much in the efficiency of your grating anymore. So that's why the design stuck with a 6-inch grating, with an efficiency about 80% at the edge of the grating and 90% in the middle of the wavelength band. And then also we did some calculations with the blue grating. Light doesn't like, blue light doesn't like glass, it gets absorbed, so the blue grating is kind of difficult to design. And when we modelled it, we found, there's a few different ways we could make the grating. We could make it a bit thicker, but a higher index of refraction. We could make it a bit thinner. And these are the different efficiency curves we get over the wavelength band. And we looked at it and said, well, it's really kind of similar. How do you pick exactly which grating you prefer? We convolved it with a figure of merit, which tells you where most of the information comes from, where the biggest gain of spectra you can get from your instrument. Convolved this with a grating and decided what kind of grating we were going to make. And here are grating curves that we've got. These are measurements compared to our predictions. Here's wavelengths, so 1, 2, 3 wavelength bands. Our requirement was 80% over our instrument, and that's pretty much what we got. So we have gratings in hand that work. We can put that in our first spectrograph if we want to do a test spectra before we go on sky. Next, the DESI focal plane and fiber run. So this is up here, going down. The cable run is about 40 meters of optical fiber between the focal plane and the spectrograph. 5,000 40-meter long cables. Before we can understand the fiber run, we look at a bit of heritage. Now, DESI, one of its earlier, it started off as a new instrument for BOSS, an upgrade to BOSS called Big BOSS. So the heritage from BOSS, this is the Sloan telescope. The way that BOSS works, you see this guy pushing in this focal plane. These are all optical fibers, short little optical fibers. And the way they position their fibers on the galaxies is they have a plug plate. This is David Schlegel, the PI of BOSS. This plug plate is about 1 meter in diameter, and you can see all of the holes in the plug plate. So they say what objects we want to observe, they go and drill the plate, someone plugs in the fibers by hand, and then they make their observation. BOSS had 1,000 fibers. If you're wondering what it looks like to plug 1,000 fibers into an optical plate, this is real time.
Give that person a raise, right?
So this works. The BOSS was a great instrument. Put a caveat on there. You can imagine.
Is there some reason why some of them are rated so roughly?
It's so that they know which fiber goes to which part, so they bundle them off so they know which spectra is which hole. You'll notice there's kind of little lines drawn on the plate, so they section it all off and then they know that within a certain section. And they also have things where if they want to observe a blue object, they can put on a tiny little plastic band to change the focal position of that fiber on. And there's lots of clever things they can do with this plate, but it is all by hand. So one observation is one plate. Here's a few of the plates lined up. People have these as coffee tables or afterwards. Here is the Boss fiber plugging team who plugged all of those optical fibers in on their first day and on their last day. Now, DESI has 5,000 fibers. They're not going to be able to hand plug 5,000 fibers into the focal plane. So what is the solution? You could hire Foxconn, but somebody's already thought of that. So instead, we move to robotic fiber positioners. Now, robotic fiber positioners, there's a few different options, all of which are installed in instruments at the moment. They're one of the oldest methods are pick-and-place robots, like 2DF at this is the telescope about 7 hours outside of Sydney. I'm going to blow this picture up so you can see how it works. Now this is the focal plane. This is a fiber. There's, I think, 400 of them. They park them around the edge, and then this robot comes. Each of the fibers has a magnetic button and a prism on it. The robot picks up the fiber from the edge of the ring and places it where it needs to be. So it picks up one fiber at a time and places it on the focal plate. And they've got 2 plates so they can switch it around and position one set of fibers as they observe with the other. But still, you pick up each individual fiber one at a time and place it on the focal plate. As I said, these have prisms on, so the light comes in from the top, hits a prism, and then goes down the fiber. Took me a while to figure that out. So this is one option, but it's still, one at a time. There's 5,000 of them. In DESI, we have a specification that we have 2 minutes between observations. Yeah, they're 15-minute observations with 2 minutes between. So we can't do it by moving the fibers one at a time. We have to move the fibers all individually, and that means that each fiber needs its own robot. So there's 2 methods. Another one developed by the Australian group is something called KIDNA, which is on FMOS, the Fiber Multi-Object Spectrograph, which is on Subaru Telescope, the Japanese telescope. And this is a tilting spine. The fiber comes in from the back through here. This is the tip of the fiber. This part here is fixed in the focal plane, and the fiber tilts around, so kind of like your arm. It points up or it moves. It tilts its way around. So it's got this little focal plane, this focal area that each fiber positioner can reach. So that's one option. Another option, first proposed by the Chinese group on the Mayall Telescope, is this little robot, and it's got 2 axes. The fiber comes in the back through here, and then here's the front of the fiber. Now this shaft rotates 360 degrees, and this shaft rotates 180 degrees. So here's this main shaft, this rotates. Here's that fiber arm with the fiber right here. So you can see that by rotating those 2 axes, you can get the fiber anywhere within this yellow dashed line. I'm going to show you a movie of that moving in a minute. So we have these 2 different technologies that we can pick from. We need our list of desired characteristics again before we can choose which one we want to use. First of all, it's going to be compact. We need to fit 5,000 fibers into a 3-degree field of view. Our focal plate on DESI is 800 millimeters, so we need to fit 5,000 of these robots on 800 millimeters. It needs to be accurate and fast. I said that we need a 2-minute reconfiguration time between observations, and we want to position them to within 5 microns. Every micron away from the target is a loss in efficiency, so we want to place the fiber as close to its intended target as we can possibly get. This survey is going to run for 5 years. Over those 5 years, the positioners will each move 250,000 times. They can't break, they need to be reliable. They're at the focal plane, they need to be both low power and low mass. Any heat you exert on the focal plane gives you aberrations. And then finally, and almost most importantly, they need to be fiber friendly. Optical fibers, these tiny little strands of glass, they don't like to be stressed, twisted, bent, poked too hard. This is one of the main things that we need to test. We need to test that these positioners are fiber friendly. So we got 4 actuators to test over these different scenarios. We have 3 rotating axis positioners, one from LBL, one from a Spanish group, one from a Chinese group, and then we also tested a tilting spine from the Australian group. Here's a picture of one of the rotating axis positioners that we tested. I'll show you a movie of it moving. This is the fibre coming out here. You can see the main shaft rotating, and then this little arm rotating as well. So you can see how fast it is and how smooth it is. I'll play it one more time.
Question?
Yeah.
The tilting arm, you don't worry about the angle it's making to the focal plane?
That's an excellent question. We'll get to that. Yeah.
Did they just do one fiber, that whole little?
One fibre per robot.
No, I mean that was just putting it in one place, or that little movie you showed?
Yes, that's moved. Well, I think it moved it to 6 targets.
Okay.
I think.
And it says 6 points.
Yeah. But it can move anywhere. So the positioner on the sky has a 3 arc minute patrol area. So anywhere within that 3 arc minutes, the fibre.
Go with that little arm.
Yeah. Yeah. And this is what that looks like. So the fibres have a 12 millimeter pitch, 12 millimeter patrol area with a 10.5 millimeter pitch. So each of these positioners has an overlap area where more than one positioner can reach. You know, we're looking for structure in the universe. So if we have any kind of bias of areas the positioners can reach to, then we see that imprint in our galaxy survey. So we want to have a nice, smooth distribution of where all of our fibres can get to. I mentioned Lemmost as one of the heritage. Here is an image of Lemmost. You can see each one of these tiny little things is one of their robots. They have a 1 meter focal plane with 4,000 robots. It looks pretty scary to me. The difference between this and DESI is that we're going to make things in wedges. So we have 500 fibres in one wedge. So we make 500 little mini instruments rather than one big focal plane with 5,000 fibres. The echidna, the tilting spine, the heritage. This is a photo of echidna on FMOS. This is the front of the fibres you can see here, and each one of them can move around. I don't have a video. In case you're wondering why it's called echidna, that is an echidna. You can see the similarity. So if we're going to test these, the first thing that we tested was how accurate and fast are the positioners. And this is the way we did this. We set up our control bench. We have a test spine. We have a reference fibre fixed to the bench so that any changes in temperature or expansion of the bench we can calibrate out. And then we have a fibre view camera, a targeting camera, to see how closely the fibre got to the target. So we program in a whole bunch of targets the fibre has to go to, and then we measure how closely the fibre gets to those targets. And we allow the fibre to move once to kind of get as close as it thinks it can, and then we give it some information back to say, actually, you need to move another 5 microns to the right. And we let it iterate around until it gets to within the required accuracy. So here's an example from this. The blue crosses are the targets that we asked the fibre to go to in X and in Y, and the green X's are where the positioner got to. You can see it's kind of close. This is the first big move, and then we give it some feedback and let the positioner get closer and closer. And you can see by the end, all of the crosses overlap, so the positioners are exactly where the targets need to be. So we compared the 4 types of positioner that we have. Took off the names of the positioner, false advertisement. And so the time to move, each one of these is a move against the log of the error. This is our 5 micron requirement. And so for example, this one, it got below the requirement by its second move. It positioned less than a micron by its second move. We have 3 positioners which all meet requirements for positioning accuracy of getting to within 5 microns. Well, this is a minute. We've added on some time for the fibre view camera. So we have 3 positioners which meet requirements for the accuracy. The next test that we can do are the positioners fibre friendly? Now the fibre system, we want to maximise throughput. We have 107 micron core fibres, which is 1.5 arc seconds at the mile. This matches the fibre size to the seeing at the mile. And our requirement is that we have 90% of the light within the focal ratio of the spectrograph, which is f3.57. The reason this is important is if you look at a fibre, here's a cartoon of the fibre, you put in light at a certain focal ratio, a certain angle, range of angles from the telescope, any imperfections in the fibre spread that light out. And so if your spectrograph, if your lenses are only designed to meet what goes in, then you're going to have lots of losses from the beam spreading coming out of your fibre into your camera. So you want to minimise the beam spreading that happens within the fibre to the spectrograph, which improves your efficiency. Things that stress the fibre, external stresses, bending and twisting. You see how that robot moves the fibre around, that's putting in little bends and twists, so that's what we worried about for the rotating axes. But also geometric effects. If you put in light off axis, which is exactly what the tilting spines do, then you get beam spreading because you're putting in different angles than if you're putting light on axis. So the two different positioners have two different ways that they're going to introduce focal ratio degradation that we wanted to test. And the way that we did this, we used an Offner relay. So you put input illumination here, this is a 20-degree diffuser. This is your main mirror we broke into to make it cheaper. Focal plane here to set the focal ratio, we input light at f4, and then over here is where you put your test fibre. And normally when you do FRD tests, you focus your spot exactly on the input of your fibre. But because we have fibres in positioners, we need a patrol area where the fibre can move around and always get the same focal ratio. And this is what the Offner does. So over here, this area, it's a circle. Anywhere the fibre is in this focal plane, within this area, it's always going to receive the same focal ratio, so we can know what comes out compared to what goes in. It might be better with a picture. So here's our input. This is that main mirror that I showed you. This is where we set the focal ratio. So we put in a 3D printed part at f4 with the obscuration from the prime focus. And so here you can see my tilting spine. So anywhere that this tilting spine moves within that area, it's always going to receive f4.9. So we can look at the light that comes out and know that any beam spreading is only due to the angle offset that we get as we move the positioner around its target patrol area. And this is what the light coming out of the fibre looks like. We put in f4, this is focal ratio. The light that comes out is a top hat convolved with a Gaussian. The spectrograph is at f3.57, so we draw a line at f3.57 since that's all the spectrograph can see, and we say how much light is within that area. So we have 95% of the light going into our spectrograph. And then as we move the spine around, we can see how this efficiency changes due to the beam spreading. And this is what we get. So on axis, we have our 95% efficiency. As the fibre tilts down, you get geometric effects from the fibre. So here's the efficiency dropping down as you get more beam spreading. If we have a requirement of 90% enclosed energy, this means the spine can only move within a 6mm patrol radius if we want to maintain that requirement, just from losses of geometric effects from the fibre. We did the same thing for the tilting spine. Again, on axis, we get about 95% efficiency. As we rotate the main arm around, we're introducing bending and twisting in the fibre, so the efficiency drops off, but it drops off much lower than the tilting spine. So the losses that we get from the rotating axis positioner are a lot less than we get from the tilting spine.
Dr. Poppett, the losses here are from twisting, right?
Bending and twisting.
Yeah.
Yeah.
Whereas the other one, it's really
geometric.
Yeah.
Yeah, off-axis light. Finally, we want them to be reliable. I'm not going to go into this too much. There's a very simple test you can do for fibres. Rather than putting in that full cone of light, if you put in collimated light off-axis, because the fibre's round, it'll scramble it azimuthally to get a donut. Any imperfections in the fibre will scramble it radially and make this donut thicker and thinner. So by seeing how the full width half max of your ring changes, you can predict the performance of the fibre in the full cone. So here's the full width half max of that ring at a certain focal ratio at the beginning of the fibre lifetime. It doesn't really matter exactly what this number is. What matters is how it changes. So we moved the positioner 20,000 times and measured that ring, 50,000 times, measured the ring, 100,000 times. So we can see that as the positioner is exercised, as the fibre is bent, any micro bends, micro cracks that propagate, we can see that it doesn't really degrade the performance of the fibre too much, which is something that we were worried about. In summary, we have a positioner that meets the size requirements, it meets the positioning requirements of the 5 microns within 2 minutes, and it doesn't degrade the fibre performance. So at the focal plane, we can put this positioner, this rotating axis positioner, I said we made it up into 10 wedges. So the positioner goes in here, this is the fibre tip, we collect the fibres at the back, guide it up, and collect all the fibres in a spool box to protect them. Within the focal plane, you can see, here's your 10 wedges in the focal plane, made up, each with those little boxes at the back. We can talk more about those later. We put a positive pressure over the front of our focal plane to stop the fibres getting dirty, to suck everything out. And then that's 50 minutes, so finally, everything else that I haven't talked about. Here's a photo of the last collaboration meeting of DESI. You can see that there's a lot of people in the collaboration. There's tons of work being done. I hope I've given you an overview of kind of how DESI works, but I've only concentrated on the specific parts that I actually work on, so everybody else in here is doing everything else. A few lists of people who work on it. There's French, UK, Spanish, all places within the US as well, LBL, NOAO, Ohio, SLAC, Michigan, Yale, Utah State are on there as well. There's a lot of people working on DESI. In conclusion, we're pretty sure the design of DESI will meet the scientific and technical requirements for the survey. All of our major systems have been optimized through trade studies and R&D. Everything I've presented here is specific things that I've worked on. There's a lot of other things being worked on too. The instrument team includes experts from both BOSS and DECAM, so we've got a lot of heritage, lots of relevant experience. And finally, a small plug, DESI Science's Cosmology. We're going to have 12 million fibre hours, but there's another 3 million fibre hours going spare, begging for the Bright Time Committee. So if anybody has their favourite Bright Time project, now is the time to put that into the DESI planning. And hopefully, we'll be on Sky in 2020. Thank you.
All right, Lynn wants to kick us off.
And this part you said
Which was the what?
which was the winning robot.
The LBL design.
Oh.
Yeah. The rotating axis LBL design. The design's by LBL. It's actually being made in Michigan.
Did your team ever consider creating their own system of robot instead of using one that's already existed, or was that something that would have probably required way too much time? Is it easier to go with an existing model than to think of a new
So we
model?
started with the design for the most and modified it. And that's the design that we kind of ended up with. There was the Chinese group and the Spanish group and the Berkeley group all working on it at the same time. The Berkeley group actually started, rather than 2 rotating axes, we started with 1 rotating axis and 1 R-arm, which moved in and out. It was kind of a scissor jack, so it moved in and out, double scissors. So it was an R-theta design rather than a theta-phi design. And it had this little cord which pulled the arm in and out. And we worried that that would break over 5 years. Yeah. And the cord would stretch. So we moved from the R-theta design to the theta-phi design, back to the kind of the Chinese starting point, and then changed the arrangement of the gears. We have DC brushless motors for gears, how they all fit together. So it's a proprietary design that started from the Chinese design. Yeah. But yeah.
Ahmed.
How did that
Yeah.
The overlap, yeah.
Yeah, so they have some overlap, so it's all controlled by software, which is being worked on. They're pretty robust, and even if they did collide, the optical surfaces wouldn't hit each other because, they point up. So, but you do kind of worry that, like an old typewriter where all the keys kind of get tied into a knot. Yeah, so somebody is working on that.
Steve, is that your question?
Well, that was, so I was curious about that too, but could you talk about the launch conditions? So the fibers, do they have a grid lens?
Nope.
It's just flat fiber?
Yeah. So originally, we've done a lot of work on the end face of the fibers, since that's where you get most of your focal ratio degradation. We changed how the fibers were held, the ferrules, the glue, the strain relief at the back. Originally, when we put the fiber in the position and it bent it around, we got tons of degradation. So we put on some strain relief tubing, so as the positioner bends around, you don't get stress points on the fiber, which helped a lot. And then also, we started with polished fibers, so you bond the fiber in a ferrule and then you polish it. Now we actually cleave fibers like they do in telecoms. So we have a glass ferrule with a UV curing glue, which is super soft, so it doesn't stress the fiber. But it's just a plain fiber in a ferrule held into the positioner.
It's not
There's no
polished with a
lenses.
dome or
No. So the prime focus corrective feeds the fibers at f4, which is perfectly fine. Fibers like to be fed between f3 and f5, and we're feeding them at f4, so we don't need anything extra at the input or output.
Yes.
What's two questions really? What's the time? How long do you expect the telescope to be on station? And secondly, on your gratings, being organic, do you expect any degradation, or do they have a certain lifetime, or what do you do about that?
So first of all, we expect to go on Sky in 2020 and have a 5-year survey. So that's analyze the data as it goes. So the first data release will be about 2 years after first light. And then the gratings, they actually put in an optical cement around the gratings to kind of seal it in. And they've done lifetime tests. No real actual lifetime tests have been done. They've been temperature cycled. Instruments are just starting to adopt VPH gratings, so there's no kind of real old data from them. The Australian spectrograph Hermes has VPH gratings that was commissioned this year, so that'll be the first one with real gratings, VPH gratings in it. Yeah. We've got one in our lab. It doesn't look cloudy yet.
Can I ask who makes the gratings?
So there's a few different. The main commercial company, there's Kaiser Optical Systems, COSY, and there's also a group called Wasatch. But from a university point, at University of North Carolina, there's a guy called Chris Clemens, and he made the gratings for Virus. He makes very good gratings.
Oh.
You mentioned your two-lens atmospheric chromatic aberration. Was that new tech, or was this in any way developed from BOSS? Or
No, BOSS does not have an ADC at all.
has it been used anywhere else, or is this going to be the first deployment of this kind of?
I think that this type of ADC, it's the first kind, but I would about
There's been
80%.
rotating plate ADCs for a while.
Not of this size.
But not of, yeah.
Nice.
Yeah, so it's a flint, each lens is a flint and a crown. So you've got the two of them, which, certainly for this size, it's the first.
Also, one more. You mentioned Euclid survey as well. You're both on the trend line. It's obviously going to be a space-based mission. I mean, is there much synergy between these projects, or what's the sort of?
There's a lot, and it depends on actual launch dates. So our expectation is that we'll be on Sky first, and we'll do all of the low-hanging fruit to do all of that stuff, so that when Euclid comes on Sky, Euclid can spend its valuable time doing the difficult science. That's the plan.
I had a question on the overall budget, and when you talk about this and we see that large team, right? You're talking about your project, which is one part of these sort of validation tests, right? There's all those other validation tests. So do you have a funding number for completed, but also to give us a sense of scale of, there's a fair amount of funding going into these design reviews before you even get to a final design.
So the full project cost is about 60 million. The Mayall costs about 5 million a year to run. It's on the order of 60 million.
And then,
Where's the money come from?
where's the money coming
It's
from?
Department of Energy, with buy-ins from hardware buy-ins from universities for science. They have about a 900k institutional buy-in in the form of money or hardware. The UK have just got their funding granted. I think they got about $2 million. So they'll do they'll buy some corrector lenses, they'll align all of that. They're buying the optical fibre and making the slits and cables, which is what they did for FLOS.
Next one.
I was wondering how you got into the engineering front of this huge astronomy mission that's going on up
Yeah.
the universe is. How did you get yourself into that position where you got to build with
There was
them?
no grand plan. It's just it's just kind of happened. So, my degree was physics and astronomy, and then when it came time to do my master's project, I was much better at experimental lab-based things rather than theoretical type projects. So I applied for a experimental type project and was given in astronomy, and was given a project testing the wavelength temperature effects of optical fibre performance. And then, like Scott said, I left, and my master's supervisor had money for a PhD student, asked me to come back and carry on that testing. So then I was doing kind of, astronomical instrumentation testing, tested gratings and fibres, and designed fibre front-end systems. And my PhD supervisor was working on Big Boss, which is the old version of DESI. So there was that kind of crossover between me finishing my PhD with him and then moving to a postdoc to work on DESI. It's just kind of doing whatever I was interested in at the time, really. Yeah, I'm kind of lucky.
On top.
Okay, yeah, so you mentioned these fibers are the size of human hair. I mean, was there any particular consideration, why is it not larger or smaller?
Well, so you match the fibre to the plate scale of the telescope. So I showed before the average seeing at the Mayall. You want the fibre to match the seeing. That's kind of your best efficiency. And so from whatever the corrector is, the corrector converts that seeing to a plate scale. So that's where the size of the fibre comes from. It's purely down to plate scales.
I also imagine, these lights probably more than likely they won't really come into the fiber, meeting that photo-internal, let's say, reflection. So you're going to have some optical loss here, right?
So you have losses purely from the glass. You have about 90% efficiency through the fibre as long as you're redwood of about 400 nanometers. Bluer than that, you go down to about 50%. But because we're injecting light at f4, we don't have too many losses from total internal reflection. The fibres can handle about f2.2, 2.3-ish. So as long as you're injecting slower than 2.2, you don't have losses from total internal reflection too much.
And your sample selection, your target selection, you want to talk about how these targets are selected for the spectroscopic survey?
That's been done at Utah, but we have targets from Dark Energy camera. We have targets from. We're commissioning a target on the Bock 2.3 meter telescope for targets.
The Dark Energy camera just put a press release out today about something.
I think they released that a few months ago that they were going to do that.
Yeah, no, I mean, they just, literally today I saw a press release from them.
Most of our targets come from DECAM.
Oh, sorry.
Is the Chilean desert the most optimum siting for the instrument, or does it matter?
So we looked at both the instrument in Chile and the instrument in Arizona. Chilean is a great site, but because DECAM is on there until 20-something, we couldn't put the instrument on there until the DECAM is finished. And there's nothing on the DESI on the Mayall in Arizona right now, so we could put the instrument on the Mayall before we could put it on the Blanco in Chile. And actually, the funding for the Mayall was diminishing very quickly. So if there wasn't a dedicated instrument to be put on it, it was likely to be closed down. So that was one of the decisions, ended up putting the instrument on the Mayall.
Are the DESI researchers anticipating finding any other findings aside from identifying those 24 or so moving galaxies? Is it more so the categorization of that data? Are they anticipating any other possible findings?
Well, that's the primary one, but actually I gave a talk at the SETI Institute in Berkeley a few weeks ago, the Search for Extraterrestrial Intelligence, and they said, what do you do with all of the spectra that just looks weird, that you can't analyze? And that could be somebody shining a laser at us. So all of the data that we would, get rid of, they're getting that straight off. So
they are doing something with the kind of the outlier data.
Yeah, and this is DOE funded, which means that we have proprietary data for a short amount of time, and then it's public. So anybody who wants to use the data in any way can. That's one of the best things about it being a DOE funded project.
All right, but let's thank our speaker again.